me just.
Right, very good. So you're on time. Our next speaker is Elizabeth Pacheco from Western Sydney University. And she's going to tell us about graph moves.
Which I'm going to write nice and big. There we go. That is better. Okay, so I will go as I promised, because that's the very least I should do, which is I assume that people know nothing about Leavitt Path Algebras. If you know something, hold your horses, please. I have a promise to fulfill. And then going on from Leavitt Path Algebras, eventually you'll find out that it's an algebra. Wow. And so it has generators and relations that are given by an underlying graph. There are moves we can do to this graph that, depending on what move we do, we can preserve certain features. And yeah, that's eventually what's going to happen. Okay, so graph moves. First, we need a graph, as suggested. And we've already pretty much talked about that, so I'll go over this a little bit faster than I would have otherwise, but only just a little bit. We do have some different dialects when we talk about graphs. So actually, my native dialect is this. A graph, gamma, is given by a set of vertices, a set of arrows, which my advisor always wished he had the courage to put A, but E is even so common that he chose to do that. Source maps and target maps, where source maps and target maps are both maps from the set of arrows to the set of vertices, and you give the source and target of each arrow respectively. So this is my native dialect. The dialect that seems to be a bit more common out in the world is this. Your graph is E, your set of vertices is E superscript 0, your set of arrows is E superscript 1, and you have the source map and the range map. And of course, if you're over in Quivers, I'll remind you what Mateos wrote, that you have this with subscripts. So we just also changed the placement, which I find a little bit strange, but here we are. And I noticed that he used S and T. So I will try to make everyone and no one happy at the same time. And for my talk, I will slightly combine the two. So I'll use E, E0, E1, S, T, because it seems like ST is more common and it is my native dialect. So I get to be happy in that way.
Also precisely my notation for most.
Yes, see, yeah, I play to my audience. Okay, so this will be my notation throughout. Once you have a graph, let me maybe draw maybe a little example over here. A random graph doing its thing. And this doesn't actually have all that I want, so yeah, maybe I'll add that guy in. And maybe this guy in. Yes, why not? Okay, so there are some terms when we talk about graphs that'll be important. For instance, this is a source. A source is exactly a vertex that only has arrows coming out of it. This is a sink. A sink is exactly a vertex that has only arrows going into it. And there are things that I dare not picture here, but you can have infinite emitters, which I like how I'm inconsistent and I switched back to cursive. That's fine. Infinite emitters are a vertex. Wow. Vertex with infinitely many arrows coming out. I'm just mentioning its existence, honestly. If you're like, oh, how much is she going to do with infinite emitters? Almost nothing. But they do exist, and we should acknowledge the existence of the beasts out there. Infinitely many arrows coming out. And you can also have infinite receivers, though I will mention that infinite emitters / sinks are both considered singular vertices. And if you're not an infinite emitter or a sink, you are a regular vertex, which is so much more comforting. Well, I guess not infinite emitters, also you would be regular vertices. I should be consistent with what I have written above. Okay. So yes, and I'll also label these guys. Closed paths of length 1, these are loops. And yes, later on I'll talk about return paths, but return paths are just exactly as you suspect, paths that return. So I will save you further labeling my picture, and hopefully that is somewhat visible. If someone unmutes themselves and says I can't read anything, please let me know, because otherwise I will do my best to try to keep this readable. Okay, so we have our graph. Now we need to construct our algebra. Okay, so we first start out with a familiar algebra that we saw previously. So I will go slightly faster, but not too much faster. There's the graph algebra. So let me write it slightly off here to the side. My notation for that would be F E, if I'm to be consistent with what I said I'd use for graph. So what that is a correct way to state it succinctly is formal linear combinations of paths where multiplication is given by concatenation of paths when it makes sense, 0 when it does not. Another way of writing it is with generators and relations. So I'll write those here. So remember that for your graph, you have E0, which now I realize I fear I'm writing a little bit small, so I'm actually going to waste paper. And I'm going to write that again. Okay, we're defining graph algebra in terms of generators and relations. I will label the relations with these guys. Admittedly, I guess to be, yeah, no, this is my native tongue coming through. I'm sorry. So the first one is this. If you have V and U, that is delta V U, V for V in E0. So combining dialects a bit, but basically if you multiply a vertex by a vertex, if it's the same vertex, you'd get just the vertex. So vertex squared is itself. Vertex times any other vertex, well, that doesn't make sense in concatenation of paths. So that will give you 0 because this Kronecker delta will be 0. The other relation is this. Okay, so here you will see a quirk of my advisor insisting that, why do you really need parentheses? You know what S is doing. So this is, I hope we can eventually speak the same language, but this is just multiply by the source vertex and then by the arrow, or multiply the arrow by the target vertex at the end, and you get E, the arrow. Woohoo. So basically, don't be silly about writing paths. Write them in a way that makes sense. These are the relations that ensure that. Okay, so if I want to go to the Leavitt path algebra from the path algebra, so here I'll mention that my generators and relations were from E0 and E1. I need to, for Leavitt, add more arrows, exactly double them, in fact. And these will be dual arrows. So this is E star such that E is in E1. So I've added a bunch more arrows. Of course, I need to tell you where they start and end, and they go in exactly the opposite direction. So the source of E star is exactly the target of E. The target of E star is exactly the source of E. So they're often called ghost arrows. You have E, and then you have this picture that we hardly ever draw because you don't have any more information. You have E star or E dual going in the exact opposite direction. Seriously, it is never drawn because you don't want to make your picture more confusing than it is. Okay, so the path algebra was just generated by vertices and arrows. The Leavitt path algebra is a quotient of the path algebra on the doubled graph. So now imagine instead of just vertices and arrows, you also have these weird guys that go backwards. It would still follow this same relation. So let me fix it here. That's fine. Then you add in these additional relations, which are Kunz-Krieger 1 and Kunz-Krieger 2. So Kunz-Krieger 1 is E star F equals delta E F T E, which means that if you go by a dual arrow, which I guess to be consistent, I'll have it be this, E star, and then you go by F. If E is not equal to F, then death. This delta would evaluate to be 0 and it disappears. If F is equal to E, so you do E star E, then you just remember that E star starts at target of E and ends at source of E. You would just have gone forwards and backwards, and you would end up right back where you started, at target of E. So this also has a nice consequence that PQ star span the Leavitt Path algebra, which I realize I hadn't actually written down up until this moment. It's going to be denoted as LFE, where F is the field that is ambient and E is the graph. So here I'm also sneaking in something a little extra. So P is a path. Q is a path. It is totally fine to take Q star. What you do is you look at your path and you reverse the order of multiplication and star all the arrows. So that was a spoiler for something that I had actually planned to say later. Then Kunz-Krieger 2. So you have this of E equals V, E star equals V, V regular. So I have to insist that V is regular, because if V was an infinite emitter, this isn't a finite sum. This doesn't make sense, at least in Leavitt. Even not in Leavitt, it turns out. If V was a sinc, then the empty sum would of course be 0. I would be declaring my vertex to be 0, which is also maybe, as you think about it, not necessarily cool. Okay, so these two relations of the path algebra, these two additional relations that we get from Leavitt, that's Leavitt. So Leavitt is a quotient of the path algebra on the doubled graph, where we have the E stars. It is not a path algebra, but it's got some path algebra vibes. In fact, cool fact is that the path algebra that you know and love, in fact, embeds in the Leavitt path algebra. That's, wait, why did I put K there? This is something proven way back in the day by Gooderl, I believe. So it's nice and somewhat unexpected. Now, if I could in fact use this fact to say that here's something that I wanted you to be momentarily suspicious of. I gave you an algebra in terms of generators and relations, which I should now actually finish my fateful journey there. That I first gave you not enough, and then I gave you more than you necessarily wanted. But giving you generators and relations, what if I gave you trivial generators? That's entirely possible. With this fact, this spoiler fact that I, of course, introduced too early, it's not going to happen that the generators are trivial. But let me show you a very quick and moderately clean proof that the generators are in fact not 0. Okay, so quiver representations correspond to modules with, and so earlier it was brought up, this quiver representation correspondence with modules, and we still have that in Leavitt path algebras. There's just one thing we have to be careful of. There's this isomorphism condition, which states this. So I'm going to state it in terms of quiver representations, though I'm still going to use M for module for some reason. And I strongly agree that yes, things should act on the right. We are right. Okay, so MV
probably also believe that people should drive on purpose.
I try to keep that under control, but yes. So here I'm kind of honestly mixing up my viewpoint a little bit. You can think of this as either a module that you're acting upon on the right with the vertex. You can also think of this as the vector space assigned to vertex W. And here are the vector spaces assigned to vertices TE. So this is for V, regular. Sorry, what? And so I'm acting on the right.
So now MV is a module.
You can either think of M as a big module, and I'm acting on it on the right with V. Or you can also think about it in terms of quiver representations, where I look at what is the vector space assigned to vertex V. But I am acting on the right, and any other actions I will do, like from here to here, in fact, let me bring up that there's a lot of content actually in this isomorphism. This is going with all the arrows that start at V. I'm assuming that V is regular, not async, so this is totally cool. And I'm going from here to here by acting with E, 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 all the different guys to get to these vector spaces.
What structure now we have here? So
And so this depends on which world you think about it. I'll go to vector spaces for a moment. This is isomorphism of vector spaces. But the thing that's very particular about the one thing that's very, very particular here is that you might think like, oh, I assigned something here. Oh, I assigned something here. But it's that this is an isomorphism via this. And in fact, going backwards, so if you have an isomorphism, you have an inverse. You can go backwards. And the coordinate-wise going backwards, going from component MTE back to here, that is the dual. That is the E star. So that is one way to see this E star is not something that I cooked up that's completely separate. It actually, it's baked into this isomorphism condition. And I thought you were raising your hand. Did I?
No,
you were stretching.
If you want, I have one silly question.
Yes.
It's regarding the definition of a regular vertex.
Uh-huh.
Because first time I saw it, it kind of felt really arbitrary that source is regular and sync is not. But is that forced by the formulation of Kunz-Krieger 2? And
that's what I would say, yes.
So Kunz-Krieger arbitrarily chose, okay, this will be my notation, and it forced which of those two would be regular and which would be not.
Yeah,
it's just kind of stuck.
Singular is exactly the case where you look at Kunz-Krieger 2 and go, oh God, what have I done? You can't sum up infinitely many guys. Even though you can sometimes in graph C-star algebras, you can't sum up these infinitely many guys in graph C-star algebras. And in Leavitt, you can't sum up infinitely many guys at all. You just can't. It's not cool. And you certainly don't want to have the empty sum, which would be 0. Like you don't want to. Yeah. Oh yes, which I'm totally getting to. But yeah, it's exactly Kunz-Krieger 2. What makes you pull your hair out? Exclude those guys. Okay. So quiver representations, which are in correspondence with modules. I will, mention that this works for. This is where I will have to narrow my view of graphs. So I'll assume that E is row finite. What row finite means is that, so I could have infinitely many vertices, and I could even have in total infinitely many arrows, but each vertex only admits finitely many arrows. I can still have actually sinks in this context too, like this, but yeah, no infinite emitters. There we go. Now we're safe and cozy in our.
But infinite receivers, why?
Yeah, that's oddly no problem. Philosophically strange, but oddly not a problem. Okay, so one way to show that generators aren't trivial is I produce a module, and the action of the algebra on that module is non-trivial. Boom. So let me give you a very silly assignment. So for each vertex, so we are going from a quiver representation is a functor from the small category of your graph to vector spaces. An assignment, like you see somewhat up here, of vertices to vector spaces, arrows to linear maps. So what I can do for my objects, one safe assignment is to just do this. Linear combinations of natural numbers. So natural numbers is my basis. I'm just making sure it's not r to the n or something like that. I have countably many of these guys. That gives me enough wiggle room that I will always be safe. And then what I have to do with my arrows is I just need to make sure that when I have f n, which is assigned to vertex v, so suddenly changing my notation over here, and hopefully that is visible online. I think it is. And over here I have f n t e. Well, I can definitely make these isomorphic because this is countably many. This is a countable basis space. This is countable basis. There is a correspondence. I know because they have the same cardinality. Choose your favorite correspondence for each e, like such that it chops things up and you're pretty much done. So so yes. So maybe I'll say pick.
Is the right sum is over all the edges emited by v, right?
Yes, yes. This is, over start of e equals v. That's what the sum is over, which I should also put here. Start of e equals v. And the map itself is e. So e in each coordinate. So you just pick e such that f n v is isomorphic to f n t e. Choose your favorite correspondence of countably many guys and build it up and you're good to go. This is a module. It's a very silly little module, but it's a module that if you act on it with v, which would be projection to that vector space associated to that vertex, or you act on it with e, which is just this random linear map you chose out of a hat that meets this condition, you will have a one-to-one correspondence. And it will act non-trivially, meaning that your vertices and arrows were not zero, which admittedly you already knew. I'm sorry that I keep spoiling myself and getting ahead of myself. This is a very well organized. Okay. So Kunstkrieger 1, Kunstkrieger 2. I guess I'll also mention back here in Factland. So we have this nice fact from Gooderl, which I should give him full credit. I hope that's how you spell it. All right. Another fact is that it's Z-graded. If you think in terms of generators, vertices are graded as zeros, arrows are graded with grade 1, and dual arrows, ghost arrows, whatever, are graded with grade -1. With that, it's Z-graded. It works out well. And yeah, that was pretty much all I wanted to say about Leavitt Path Algebras, the breakneck introduction that hopefully was gentle enough. Are there any questions here? Okay, either everyone's asleep or everyone is lost. One of these two, no in between. Okay, so some of you have seen spoilers for this next part, but hopefully you will find this next part overall a bit more interesting. So I've given you generators and relations, which are dictated by this underlying graph, and that's fantastic. But as you might suspect, there are many different presentations for any group or many different ways of giving generators and relations that reveal the same underlying algebra. So you should entirely expect for two different graphs to produce the same Leavitt path algebra. And to draw a very trivial and classic example of that, here's one. This and this have exactly the same Leavitt path algebra. They have different generators, they have different relations, but lo and behold, if you beat this enough, and honestly not that much, it screams pretty quickly, you get the same algebra. And it just so happens that these graphs are related by a very popular, and quite frankly, the best move, which is outsplit. Let me tell you about outsplit. So okay, so outsplit is a move that you do to a vertex that has, in order for it not to be trivial, it needs to have at least two arrows coming out of it. So you can even do this in the case of an infinite emitter, but I shy away from that because I am frightened, easily scared, but I'll tell you how to do it correctly. So let's say you have E and you're translating it into, let's change the letter. Let's change it to F. If I put a subscript O, that's not going to help you. Okay, so you have your original graph, and this is the outsplit graph, which hopefully that is large enough to read online. Okay, how do you do outsplit? You pick a vertex. Yeah, I'll go with W. You pick a vertex W and partition S inverse W. So now I suddenly use parentheses because what this is so S inverse will go from the arrow set to the set of, well, let's see. Yes, S, I'm looking, yeah. So to remind you, S goes from arrows, sorry, wow, vertices to arrows. Oh God. Oh God. Wow, my brain fried. There we go. Okay, S, arrows, vertices. Yes, it tells you the source. So now I'm going backwards. I'm saying what arrows started with W? Pre-image. Wow. Okay, I partition this into n sets to be consistent with what you see here. Yes. I guess actually here I'll put just ... epsilon n. Epsilon I is non-empty.
Why you need at least two arrows?
Yeah, I mean, you can, if you do the outsplit on a vertex that has only one arrow coming out, congratulations, you've done nothing at all. I mean, I guess you can feel like you've done something, but you've also done nothing. Okay, so you cannot partition this into more arrows than you have coming out. But once you pick a vertex and you pick a partition, what you do, so F0, that is E0 minus W, but then you union one vertex, and I'll try to be consistent. They have them numbered according to how many elements of your partition you have. So you basically partition your W into new guys. And then I need to tell you the arrow set, which I somehow started writing in E, so now this is a super long F. Okay. E1 minus...
Follow his columns by equality.
Oh, yes, you're right. Both, really, by definition. S inverse W. That's a set, so that's fine. But then I have to union E1, En, start of E equaled W. Okay, so, oh, wait. No, I partition the arrows coming out of W. So this is the other. I duplicate the arrows coming in. Sorry. Very convincing covering up. There we go. All right. So I look at my arrows. I mostly keep all of them, but I take away the arrows that end at W, and then I duplicate them. So for each arrow E that previously ended in W, it's replaced with N copies. Then I honestly think the next part will be clearer by picture, so let me show what I mean. Okay, let's say this is W. And then let me partition the outgoing arrows into two different sets. So I have, these are all the arrows coming out of W. I have one set, I have two sets. So over here, I will have W1, W2. And for the arrows coming out, I partition. So let me first actually draw these guys. So hopefully the picture is clear enough to see, and actually let me auto-tune it slightly. I don't know if that will help. Okay. And I duplicate the arrows coming in. This loop I will handle in just a moment because it is in both cases. It's both an arrow coming out and coming in because it has the sacred job of being a loop. Okay. These guys duplicate.
What is the partition?
The partition is I gave these two outgoing arrows a single tick mark, and these two outgoing arrows two tick marks.
Kind of not clear.
Oh, sorry, is it not clear? Like,
Yeah,
oh,
2 marks are
okay. So yeah, it's this loop and this top arrow, and then these bottom two arrows. Okay. And another thing that is unfortunately really unclear with my picture is that in this map, the source is preserved. So let me actually label this edge E. This edge previously went into W. So E1, E2. It still has the same source, let's say V, but it goes into both of these guys now. It goes to both elements of the partition, W1, W2. Okay, now the loop. The loop we have to treat in the same way. So source is preserved, but target is duplicated. So I partition this into the one that ended up being the first one. So source is preserved, target is duplicated. Source is preserved, target is duplicated. You get these two arrows from this one loop.
But here it's very simple. When it says source is preserved, source already vanished. Source was turned from W to W, but you made a partition.
Yes.
So this was your choice of new source.
Yes. But the yeah.
I'm saying it because it's going to give me explicit.
Okay. Yeah, no, it's if you state it carefully, which I honestly don't know if I've managed to do super carefully, but it's really exactly that you partition the arrows coming out, you duplicate the arrows coming in. It's just, for me at least, it definitely took some time in the case of a loop where it's both an arrow coming out and in to see how it works. But yeah, for the arrows coming in here, they're just duplicated. You preserve their source, they go to both of these guys. For the arrows coming out, it's not hard at all. You choose the new source based on the partition of W. So that's why we had this loop, this guy, this guy, this guy. To further go into the loop though, yeah, I have to duplicate it to go into the other elements of the partition because it only comes out of here, but then it has to go into W1 and into W2. So that is the outsplit move. I welcome questions on it. We're going to talk a little bit about the map. So the map is pretty much really great because to me, it's just taking Kunstkrieger 2 and saying, what if I had more vertices, and just prying it apart and then adding a couple more arrows coming in so that you still preserve the adjacency relations that you want, the path algebra things that you want. So from E to F, V goes to V for V not equal to W. I guess also I should mention that V is I'm always thinking of V as a vertex in the V is a vertex, but then W, remember we took away W here, it goes to W1 plus all the way up to Wn. In the example, it was W2. And then E goes to E if the target of E was not equal to W. And otherwise, E goes to, so if the target of E was equal to W, then it had to be duplicated. So it goes to E1 plus En.
I have a stupid question.
Yes.
Is it a popular notation, or is it a mistake that at the very top you wrote?
It's possible that we learned about algebras.
Oh, this is, oh, you're right. I should definitely put this being Leavitt because I can't take sums and graphs. That's not cool.
But in
Fair
fact,
point.
this is a very, very good question. It's not a stupid question. Well, I hope to explain it later on, that in fact, the morphism of graphs is from F to E.
Oh,
And the
okay.
point of our induction gives you precisely the map Elizabeth is right.
Okay.
So this was not a stupid. Okay.
Okay. So I should make this claim. Outsplit, so the reason why I say outsplit is so fantastic and so wonderful and is the first example that anyone should do is because it preserves the Leavitt Path algebra. Everything about it. The grading, all structures that you want, you get it on the nose with this. So if I'm giving you this map, I should...
It's an honest to God isomorphism.
Yes.
So I should be able to provide an inverse, right? Right? You cleverly asked to lead into my next part. Thank you. So the map going the other way is pretty much what you would expect. So maybe let me provide I'll over here, provide the inverse in the parts where it's interesting. Because most of the graph, honest to God, matches up. Like there was outside of this bubble, the universe was calm. And then inside of this bubble, you perturbed things. You messed with nature. Yes. And so for the local surgery going backwards, if you have Wi, what you do is you send it to the sum, E star, where E is a part of the ith element of the partition. So you exactly send it not to all of W. Remember that W is equal to EE star for all of them coming out, but you send it to part of them. So then if you look at this sum, W1 through Wn, and you've sent all of them back, well, in their sum, you would exactly get W because of Kunstkrieger 2.
Okay, so we should, in fact, think about outsplit in terms that the partition of outgoing arrows gives us a partition of a point.
Yeah,
this is exactly what we're doing with this assignment.
That's pretty much exactly how I think about it. I think about just like V is an idempotent, so is EE star. It's something that when you multiply it by itself, you get the original thing you started with. That's thanks in part to Kunstkrieger 1 as well. But yeah, you take your vertex, chop, 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 you pry it apart into pieces where some of the arrows are coming out of this piece, some of the arrows are coming out of this piece, but then you had to figure out what to do about the incoming arrows, and your choice was to duplicate them, so that as V was adjacent to W previously, now in the new world, V will be adjacent to all of the guys that you split your W into. And so this is where identity will work for all of these guys, but for these guys, each EI, well, yes, each EI you send to E summation E star E in epsilon I. And let me make sure that makes sense. Does that make sense? Because yes. Okay, let me show you the picture to help justify this. And maybe zoom in. You really needed to see my ugly picture super close up. But remember that E1, E2 regardless of even if we were talking about this loopy guy, which I chose not to label for reasons unknown to me, but this ends at W1. This ends at W2 because I partition the arrows going out, but I duplicate the arrows going in. This keeps track of the new endpoint. So over here, this EI is part of this E, but I need to make sure it's the right part of the E. So I multiply it by part of the vertex W. But this does keep track of the.
Well, I think that's confusing because the sum is over E, and then it had E.
Oh wait. Oh wow. Okay, that's maybe too many E's. Okay, so let's change that. How about I change this to F?
Yes.
That will.
You know, the end of E doesn't have to be the beginning of E. And
There we
this
go.
is already very confusing, yes.
So to each E, there was this sum. If you're going backwards from a particular element of the sum, you just have to be sure to, you go back to the honest to good singular guy it goes back to, but you have to multiply by the end that it would have over here, which is given by Kunstkrieger 2, basically. Okay, so it's basically, remember that EI ends at WI. So this is exactly EI WI pretty much, just mapped over to the previous universe. Okay, and this, by me not doing much beyond this, and then saying, look into my eyes, believe me, I promise you, this is truly an isomorphism. Basically, from a little bit of Kunstkrieger 1, we can't entirely shove that out of the picture, but Kunstkrieger 2 really shows you the way. Okay, and yes, best morphism. Okay, but as was noted by your wonderful questions, there was a choice made, like, oh, sinks are awful, but sources are okay, I guess. Yes, because Kunstkrieger 2 and because things are really non-commutative, but we could play this game exactly by switching our viewpoint. Why are we partitioning outgoing arrows? Why not partition incoming arrows? Because this won't be a isomorphism of the Leavitt Path algebras, but it will preserve more structure than you might expect. So, insplit. Oh my God, it's okay. Sorry.
And then please make sure you talk about shift.
Okay. So, suddenly going at warp speed, insplit is exactly the same game, but instead of partitioning the outgoing arrows, you partition the incoming arrows. You do the same duplication though. Instead of duplicating the incoming arrows, now you have to duplicate the outgoing arrows. And you have to be similarly careful with loops. The only difference, so pretending we were doing an insplit here, which doesn't make sense in this picture, if you were insplitting and this was a loop, yeah, you know what, I'll draw a picture of an insplit. That's great. Okay, so if you have this and I put these in one element of my insplit partition and these in the other, this is how the insplit would go. I have two guys now, and these guys come into here, take care of the loop in a second. These guys come into here. I have to duplicate outgoing arrows. So 1, 2, 3, 1, 2, 3. This guy is in the providence of both. So it only comes into here, but it has to come out of both guys. So I have to add an additional arrow here. Sorry. Exactly wrong direction. It only comes into here, but it has to come out of everything. So, wait. Oh God. Comes into here. Nope, my first one was right. I am so sorry. I was panicking. One more time because I definitely got myself confused there. Endpoint is preserved, but guys that emanate from are duplicated. So it only ends here. That's why you see it only ending here, but it has to come out of all other guys in the partition, namely the singular one. So it's exactly kind of what you see here, except with this particular arrow reversed. The start was preserved as W1. but it had to go out to all other vertices. Here, the end is preserved, but it has to go out from all other vertices. So exactly this arrow is reversed.
And a quick comment, if I may.
Yes.
So here we don't carry the partition that some of the sets can be empty. This is perfectly
Yes.
okay, because it has nothing to do with the second figure. And another thing I wanted to mention is that in the outsplitting, you can handle infinite meters, but the point is that when you do the partition, this infinity is located at just one subset. You cannot partition your infinity into a bunch of infinities. Just have you assign infinity to one of these vertices that appear in the partition. And then things work if analogous forms.
Yeah, you preserve basically the number of singular vertices, aka bad vertices.
Yeah.
But why have bad vertices at all? Just saying. So that's insplit, shift. So I will say, when compiling this talk, I know that I have been greatly inspired by this paper of Soren and Ruiz, which was refined graph moves in C-star algebras, and that was fantastic. But then I got to learn that Soren apparently, shift might be news to him. So that's something that seems to come from the Leavitt side. So it's interesting that both people are working to meet in the middle, and hopefully the cave is getting thinner and thinner and thinner, and then one day we'll break through and have daylight. But yes.
Could you say what insplit uses? Because
oh yes, sorry, that's a very good question. So insplit, not an isomorphism. What it preserves though is Morita equivalence, which was something that I will admit until yesterday I was like, it preserves Morita equivalence, and then I'm like, how do I prove that? And since we have a lot of cultural Catholics here, bless me, Father, I have sinned. I was prepared to confess, like, how do I know this? Is this folklore? But I found a proof of Tom Ford. So if you are curious and you would like to see on the nose what are the bimodules and whatnot, I can show it to you, but not right now. I'm so sorry, but I have it. It exists. It's not just folklore. Okay, insplit preserves Morita equivalence, which is the category of modules.
But what is irritating about insplit is that we couldn't relate it to any more.
Well, I mean, you know where the pieces of the graph go, but it's not a Leavitt isomorphism.
In other cases, when I for instance, I perform this derived graph construction, I get something which is Morita equivalent. Well, then I have a homomorphism of graphs, which induces embedding my graph sister algebra into the Morita equivalent.
For outsplit, you have no reason.
No, we have outsplit. Oh, outsplit is a longer story. I'll answer this in detail. But from insplit, we couldn't find anything. It just gives you Morita equivalence, but I see no morphism between algebra.
But you say you couldn't, so you still can't? Or?
No, we couldn't do it, and I don't have an overall theorem, but nothing obvious work.
Okay, I'll mention one verbally because this is actually not bad. So you mentioned sinks are bad, but sources are cool. Yeah, sources are cool. In fact, one move, source elimination. Look at a source, say, today you die, chop it off, send those pieces to 0. That is a Morita equivalence.
Okay.
So, and the map is exactly what you think it would be, because what else could it be? You just send those pieces to 0, and it's cool. Okay, shift. Shift is a very different flavor from the moves I've said so far, because both outsplit, insplit, and source elimination, which only exists in the air between us, is you pick a vertex that meets some condition, you do something. Shift, you pick 2 vertices. Change. Yes, 2 different vertices. So V, W, V definitely not equal to W. And the conditions you need to meet are that the target of E for the start of E equal to V, that set, is a subset of target of E. Why did I start putting parentheses? I'm sorry, I'm just panicking. Start of E equal to W. Okay, so by that I mean pictorially. So V, W. You look at these 2 vertices, you look at all the arrows coming out of them. One of those targets has to be a subset of the other one. It can be exactly equal. And of course, it can be exactly equal, but you can't have one having a little piece outside here, one having a little piece outside here. That would not lead to a valid shift moved. Once you have that, so you not only need these targets to match up, but you need to be able to match up these arrows bijectively according to their target. So this, ha ha, ha ha, ha ha, ha ha ha, ha ha ha. So hopefully I said enough ha's in case the picture is unclear, but this is a perfectly fine matching. But just to show you a non-example, if I had two arrows going here and one arrow coming here, and then maybe, okay. So for this V and W, yeah, the targets of arrows coming from here is a subset of the target of arrows coming from here. But I can't match these arrows up bijectively, because as soon as I match this single arrow to this single arrow, I don't have another arrow from W to work with. So theta has to take arrows that emanate from V and match them up to arrows in W that have the same endpoint, and it needs to be one-to-one. It needs, yes, not injective, not necessarily onto, because W can have more guys coming out, but it needs to be one-to-one. Okay, once you do that, so generally W can have more arrows coming out. You choose to erase these guys that have been matched up. You keep these guys, and for these guys from W that you took away, you say, oh, I can get to the same place by adding another arrow that goes from V to W. So I've clearly scribbled on this picture a lot. Let me show you what the result of shift would be. Oh, sorry, from W to V. Okay, and now I've lost all sense of time, but let me show you what it would look like. You erase from the guy that has possibly more arrows coming out of it in the matched up way, and then you add an arrow from W to V so that your path of length 1s were replaced by path of length 2. This ghosty path was replaced by whop whop, that path. So this is a move that seems to have been figured out by Leavitt people. Can I give credit? No, I honestly don't know who came up with this, but whoever they are, bravo. But this is, yes.
Do you know what screws up when the inclusion does not appear? Why can't you just eliminate partial subset of arrows?
And so, okay, sorry, you're saying up here. What goes wrong?
Up here, for example, if you had an arrow from V going to someplace different.
Huh.
It's related to
Yeah.
You see, the point is that you want to replace all these arrows by paths of length 2.
Yes.
And somehow you have to take care of everything which is coming out of V, otherwise the second close figure wouldn't work.
Okay,
So you cannot have a path which is not matched and replaced. You cannot have an edge which is not matched and replaced by a path of length 2.
But you can just, no, but I don't think if you can just look at the partner, you can just look at the matched out parts.
Yeah.
And do this construction only for those. And
yeah, we
what
could
happens then?
produce any kind of
You
reminder.
can do this move, whether or not V has any other parts that are not targets of but you can do this construction.
I see what you mean, but I do think it has something to do with Kunstkrieger too. Like the fact that the paths that come from here.
I mean, it's a construction of the graph. So you can just write the additional arrow from V to somewhere else. Not.
But to somewhere else where it cannot be met by an arrow from W.
Yeah.
Okay, but then this is, I think I just answered it. If you cannot match it like this.
Yeah.
Then you'll not be able to do this replacement. You have to
You
have one
want
response.
this replacement for this particular part, but you can for the parts that you can match.
So
Yeah, but you have to add up all of them with a second figure.
So one of the things also is that, so shift, it destroys the grading because I've clearly
Yes.
replaced paths of length 1 with paths of length 2.
Yes.
So, but despite destroying the grading, not only does it preserve the Merida, it not the graded Merida, obviously, but the Merida, it's an isomorphism of
Yes.
Leavitt Path Algebras. So the reason, a good reason I think you'd want to have that these arrows are replaced by these guys where you don't have extra bits that weren't matched coming from V is that with this particular matching, I can go backwards. The way I can go backwards is that, let's see, I can look at, yeah, because V and W would now have different targets. And so if I can look at all these paths of length 2, and I can go backwards here to replace them. Like I can go safely from one to the other, not in a graded way, but in a way that remembers everything. Versus I think if you did the construction you were talking about with valid matching, but I don't think you would be able to then safely go backwards. I don't honestly know exactly, maybe it is a cool graph move, but I don't know exactly what you would get. And I'm suspecting it wouldn't be an isomorphism of Leavitt Path Algebras.
But could you please write these new vertices and new edges in the shifted graph and the maps?
Okay. Oh God. Okay, so let's see. If we're going from E to F, so I realize maybe I should put Leavitt, but I also have a minute left. And not even that. Okay, if I'm going from E to F, so the arrow set, sorry, the vertex set. So this is the shift. And this is exactly equal to my previous vertex set. No change there. But what happens for the arrows is that I take these guys, I subtract. So I didn't actually write it down here, of course, but the bijection that matches arrows to here to arrows here is theta. Theta goes from the set start of V to the set start of W. Oh, yes. Oh, yes. Yes, yes. It goes between these guys in a injective way, not necessarily hitting everything in here, but then you take theta of S inverse W, V, sorry. You remove these arrows. So remember, when I map it over with theta, they are now starting at W. I erase those arrows and I replace a single arrow, F, starting from W and going to V. So where, yeah, I should tell you that start of this guy is W, target of this guy is V. And hopefully realize that that actually needs to be made visible. There we go. And now I'm 20 minutes over what I should have done, a minute over what any God will allow. And I'm so sorry, but I'll mention other moves that are kind of interesting, but I won't say what they are. Kunstfleiss. That seems to be something that graph C-star algebra people have figured out is an isomorphism. Like if you have a graph and you just glom on this monster as if that's cool. In Leavitt, we're very confused about it. It's an open question on Mark Tomford's wonderful website. I became such a huge fan of Mark Tomford in preparing for this talk after he actually explained Morita equivalence. So yeah, that's a move that graph C-star algebra people know makes sense. And I look at it and I'm frightened and I don't know what to do. I don't know how to make sense of it. There's another thing called enclosing a cyclic component, which seems like Kunstfleiss on steroids. Ask Soren if you see him around. He's a nice guy. He's lovely to talk to. What even was that? There's also these Krieger moves, which I don't even know if you can call them moves. There's some kind of god-awful algebra construction that it's something else where whenever I saw Soren define them in advanced moves, they're clearly advanced. No pictures. no pictures. This is why I like Leavitt Path Algebras. I like that it can draw silly pictures, and that's actually legitimate mathematics. But there were no pictures with the Krieger moves, so I can just say, they're a scary boogeyman in the background. They exist, doing something. I don't know what. And yeah, then there's expansion and contraction. And my advisor actually has a whole theory that I can mention to you at lunch about these moves that you can do on a graph at loopless non-sinks that preserve the Morita theory, which if you add enough sources, because that's totally cool and we don't care about sources in Leavitt, you can even preserve the graded Morita. So I had so much to say, and I thought I was going to have enough time. And that literally has never happened in my entire life. Why do I keep thinking that? I am so sorry for taking more time than I intended. I will end it here.
And Elizabeth,
Mhm.
you can allow me to, and Professor Lange can wait a little bit. Put a piggyback on her talk. Yes, it would be much easier for me to do it right now. After lunch. Is that
Oh.
okay?
Oh, okay. I will get this out of your way. And-
I need your
Oh.
slides.
Oh, okay. Well,
And
my
I need your
slides-
phone because I'll be speaking.
let's see. So let me try to keep this in order.
Not these, this is but what you wrote.
Hopefully I'm going to
Yes.
start and just say,
Hmm?
I want to only write or I want
I'm going to write, yes.
only write.
Yeah.
Okay. This and outsplit and insplit and shift, and this was trash. All right. Going from first to last
Yeah.
to most recent. It's there. Have fun. Let me move this.
Don't take your.
Oh.
Right.
I'm so sorry.
And I need your
I'll
phone.
gather. Oh,
Okay, good.
there's plenty of paper left.
Good. All right, so here everything is visible. I hope I'm still audible. Yeah, so let me give you an extremely quick background. Well, when you have a graph E and you have a graph F, well, you can consider two types of morphisms between the graphs. One is the usual graph homomorphism, as you know it from school. Edges to edges, vertices to vertices, sources and targets are preserved. And if you throw in a bunch of conditions, well, then it contravariantly induces a homomorphism between Leavitt Path algebras. Okay? So we have a contravariant functor. On the other hand, you might have a path homomorphism of graphs. Let me skip explaining the details, but basically then what can happen is that you map edges, but not necessarily to edges. You can map edges to vertices, you can map edges to long paths, whatever you want, but you still have to preserve source and target, and you must have a certain concatenation property. And then in this universe, if you have a path homomorphism of graphs, which preserves some properties, okay, then you have a category equipped with a covariant functor to the category of algebras, and here it covariantly induces a homomorphism between Leavitt Path algebras. Okay, so that's the background. Now I go back to Elizabeth's slides, and it so happens, and it's actually very beautiful, is when you look at this shift move and the formulas, well, we finally didn't write the formulas, but basically what happens is that these edges which are gone are now mapped to paths of length 2. And this, in fact, defines you a homomorphism, a path homomorphism of graphs, which satisfies all our axioms. So it covariantly induces a homomorphism of Leavitt Path algebras. And then there is an inverse that you can write to it, and it involves adjoints, okay? And this is something which we are currently working on. We call it extended covariant functoriality, in which what we are doing now, not only that we map edges to paths, but we map them to paths in extended graphs. And we no longer assume that vertices are mapped to vertices, because vertices can be mapped to be sub-projections of vertex projections, okay? So it started very recently, and we started writing about it. And this is precisely where motivation was, that in certain circumstances, when we know that our morphisms induce isomorphisms, well, the obvious question is, what are the inverses? And because my morphism is given in a combinatorial way, well, how about the inverse? Is it also given in combinatorial way? And the answer is yes, but the combinatorics involves gauss edges. So this is work under construction, so I don't want to put it officially into my slides, okay? But this is exactly what we are working on, and we have this joint new paper under construction, okay? But that's not the end of good news. So this is about shift. Now, another cool thing Elizabeth was telling about was outsplit, okay? Outsplit, where are you? Insplit, I don't like you. Outsplit, yes. Well, I mean, it's not a morphism, it's not isomorphism. Come on, it sucks. Insplit sucks. It's just Morita. Okay. So now when you look at outsplit, you see, when you look at these two graphs, in fact, the morphism that we have goes from this graph E, from the outsplitted graph to the initial graph, we have a morphism. Basically, whatever she duplicated, I put back as it was, okay? But then when you look into this formula for the pullback of this graph homomorphism, that's exactly the sum that Elizabeth wrote. And now again, the inverse, which is given with the help of the adjoint, this fits into our picture of extended covariant graph homomorphisms, okay? And what else did I want to say about it? So this is what I want you to bear in mind. And in fact, this stuff with the shift I will use in my talk. But this is also very interesting. And well, when you look at this construction, well, there's another thing I wanted to mention, but I didn't want to disrupt your talk, so I shut up, I refrained, and I'm doing it right now. This is really a very funny construction, because on one hand side, it's an outsplit. On the other hand, this is a line graph construction, which for regular graphs can be called maximal outsplit. And you have maximal outsplit when you simply have n arrows and you partition them into n subsets. So there's only one way you can do it, one arrow per subset. That's a maximal outsplit. And it turns out that if you take a regular graph and you apply maximal outsplit, a regular graph, this is precisely the line graph construction. And the line graph construction, let me remind you, it works like this, that if you have a graph and you want to make a line graph out of it, then you say that, all my edges are now vertices, and all my new edges are paths of length 2. And then it's kind of obvious that the first part of my path is my initial vertex, and the second part of the edge of my path is my target vertex, okay? These are line graphs. There's a whole combinatorial yoga about it, okay? These graphs were called completely insanely by Rayburn dual graphs. It has no sense. There's no duality. So we refuse to use this terminology. We looked up what people in combinatorics are doing, and they call it line graphs. Well, but okay, for regular graphs, I'm happy with maximal outsplit, because Elizabeth has been working on me to convince me, and she succeeded, okay? And to make it even more funny, if you look at the derived graph construction, and you take your more or less obvious derived graph construction of your group being Z2, you apply derived graph construction, and lo and behold, again, you get this graph. So like 3 different ways to describe this move: maximal outsplit, line graph, and derived graph construction. And all the time you get the same picture here with this Mickey Mouse graph appearing. And this is what I wanted to add. And please bear in mind this shift, because I will use it in my talk. And the outsplit, I'm so happy about it, because it substantiates our theory of extended graph homomorphism, which we are currently working on with Elizabeth and others. Okay, thank you so much.